Okay. Hi, everybody. We continue our work discussing about control design, toolkit, and Kalman filter. In this lecture, we shall talk about Kalman filter dynamic models. When you read about Kalman filter, usually you face a famous sentence saying that this is a model-based algorithm. So there is a mathematical model which is used within this algorithm in order to carry out a specific task. In Kalman filter, we have two dynamic models. You can select either of them, though each of them has specific application areas. The first one is the dynamic model with constant velocity, CV model, and the other one is constant acceleration model. The dynamics of the constant velocity and constant acceleration is defined by the transition equation of the states and the transition equation of the uncertainties. Mostly, it is defined by the A matrices. Let me remind you with that which we discussed in one of the previous lectures. If you look at this equation here, it represents how the state at time step k plus 1, what it equals if we know in advance the state at k, and also we know the sampling time of the time step, and we know the velocity at a given step. X at k plus 1 is equal to xk. This is the previous one, this is the new one, plus the rate of change, the differential, multiplied by the sampling time. This Wk represents an error which takes place as a result of velocity change. The velocity, as you see in the second equation here, at k plus 1 is equal to the velocity at k. We assume that it doesn't change by time. But in reality, there is a small minute changes, random changes of velocity, which appear as a noise This noise is represented by the term WK. This is the process noise, which results as the velocity changes. Now, if we use the coefficients of this equation and this equation, we can get the elements, the values of the elements which compose the transition matrix. The coefficient of Sk is 1. Here it is 1. Of the velocity, delta t, it is delta t. And the second equation, there is no xk, so it is 0. And the velocity here, and the second equation has a coefficient 1, it is given 1. So the matrix A or F, it is also called F. By LabVIEW, it is called phi. Anyhow, it is equal to 1 delta t 0, 1. This is the transition matrix, and this transition matrix is taken from the transition equation of the states. But here, as you see, we assumed that the velocity is constant, and if it appears randomly as a noise. This is called CV model, constant velocity model. Let me tell you also one thing interesting here. X here, it is a vector. It represents the number of states which are included in the system. In another way, the variables of the system. The equation shows how all these variables vary by time, step by step. Because they are variables and vary by time, so of course, if we know the initial value and we know the velocity and the length of the time step, we can find the displacement which took place to the variables. Now, if we add the displacement to the initial values, we can get the new value. This applies for tracking systems and also applies for any variable, irrespective to its nature. Suppose we are talking about temperature and viscosity. Here also, when we talk about x dot k, we mean by that the rate of change of the temperature or the rate of change of the viscosity. And if we talk about a motion, of course, this has another meaning, which is tied with the motion and the position of the moving object. So generally speaking, this equation applies for any set of variables irrespective to their physical nature. The second model is somehow more accurate because it considers that the acceleration is constant and not the velocity. So if we again look at this equation here, we see that the state at instant or at step k plus 1 is as before. It is equal to xk plus x dot k multiplied by delta t, but we have added also another component, half of the x2 dot k t squared. x 2 dots k here to the power of 2 dots, this means acceleration. So we can define the position at the new step by knowing the position at the previous step, knowing the velocity at that step, and knowing the acceleration, which is considered to be constant. So here in this third equation, x double dot at instant k plus 1 is equal to x double dot k. So the acceleration is considered to be constant while the velocity changes. The velocity at the new step is equal to the velocity at the previous step plus the acceleration multiplied by delta t, as the velocity is the integral of the acceleration. These two models are frequently used, and the engineer or the designer has the choice to select either this model or this model depending on the situation. How he selects that we shall know just now. So let us go back to our example here. As you see, here is a state space model. We construct state space model, and to construct this state model completely, you need to define the matrices A, B, C, D. I have taken the matrix A, as you see, as one dimension. This is one-dimensional array with A equals 0.1 only. This is matrix B, and this is matrix C. D is equal to 0. Now, these coefficients are taken from the transition equations which I have shown you before. The output of the state space model is shown as a state space model here. This is the matrix A. This is matrix B, the same values as here. This is C, and this is D. This is shown as a cluster, which includes all these elements together. To know about this state space model, which was created, I used this function, which gives information about the number of states there and the dimensions, inputs and outputs. So here we have an indicator as the number of inputs, the number of outputs, and the number of states. If we go to the front panel and run the program, we will see that the number of inputs is 1, the number of outputs is 1, the number of states is 1. Here it is shown as one-dimensional array, not two-dimensional array. Now, we know about this model. I have also drawn the step response graph for the same model to see the state trajectory graph. The state trajectory graph, as you see, begins with 0, and exponentially it goes up and up and up by time. This character shows you that the state by time increases every delta t. You add every delta t by multiply it by the velocity, you get a new value, and you add these values from a step to another step. So at the end, you come to an limited value. This is the characteristic shape of unstable dynamic system. Also, I have taken the cluster which represents the state space model here, and also I used a useful also function to see how the states change given an initial value. I have given the initial value from 0, from 1. Let me see, and the time is given, here it is, again I go back. The time is given as a constant beginning with 0 with a division to 1 and a length of 30. Here the length is 30 because I don't want to see it up to infinity. And each element here 12, 14, 15, 16, and so on. And as you see, this is the response of the state beginning from 1. This is 0, this is 5, this is 1. This is the initial value. Of course, if I change the initial value, here let it be, for example, 4. So it will begin changing from 4. But you will see now it is 4. This is 20 now. This is 4. And it goes up also as the same character as we have seen above. Here, as you see, we are talking about the position. We have only one variable because we have one state, and we cannot see the velocity and the effect of the velocity. If we go and also to be sure and check the position of the pole, which we have here, this is the imaginary axis, this is the real axis. It lies on the real axis at a distance of 0.1. This is positive, which means that the system also is unstable. Okay, now let us go and look at this model again when we include the velocity in our interest. That is more realistic case. So we go here again. Sorry. This is the second example related to constant velocity Kalman filter. Okay, so let us go to the block diagram. Here is the state space model which I have created. It is given a sampling time. So this is a discrete. And here are the matrices. Matrix A, generally, which mostly affects the dynamics of the system. Here, these coefficients, this is the 1 and this is delta T, 0, 1. So these values are taken from the equation which I have shown you. Delta T is taken as 1. B is defined, as you see, half delta T squared, which is equal to half, and this is 1, and C is 1. If you look at the matrix here, it is two-dimensional. So what do we expect? We expect to have two poles, and we have two variables. One of the variables represents the position, the distance, and the other variable represents the velocity and how it's changing. We assumed here that the velocity is constant. We're still working with this framework. If we go now to the block diagram and to illustrate what we have, first of all, let me tell you here, I have taken matrix A, I have found its eigenvalues. And the eigenvalues should be equal to the first and third coefficient. They should be equal to 1, 1. Anyhow, where they are, here it is. Eigenvalues 1 plus 0i, 1 plus 0i, which is 1 and 1. They are here, the same. Of course, you can judge about them by eye, but I am trying to show you how they are calculated. The state space model, as you see here, is given as a cluster. This is the A matrix, exactly with the same elements. This is the B matrix, this is the C, and this is the D matrix. I have converted the state space model to transfer model, transfer function model. Of course, as we have two variables, so we shall have two roots. And as you see, this is the denominator, and one of the roots will be, as you see here, we shall find the roots here. These are the coefficients, but not the roots. But anyhow, the system is still to be unstable because we have one coefficient negative. Now, if I run the program, let me run it for you. And now go back and look at the state trajectory graph, where it is. This is the state trajectory graph. This is the, sorry, where it is the state trajectory. Yes, here is the output. State trajectory graph. If I click it, you will see that we have two variables. One of them represents the distance or the position, and the other one represents the velocity. As you see, the velocity here, as we all assumed in advance that it is constant, but as you see, really, it is changing with a very small slope, telling that the velocity is not constant as we have assumed, and it is changing, but changing very smoothly. This is the model which we usually use when working with Kalman filter with a model of constant velocity. Let us go and see how the dynamics of the model look like if we work with constant acceleration dynamic model. This is the constant acceleration. So we have three variables. We have the position, we have the velocity, and we have the acceleration. But the acceleration is assumed to be constant. Though, also, in this case, this is just an assumption, but in real applications, the acceleration may change. And so, as a result of the jerk effect, there will be a noise. These coefficients of matrix A taken from the transition equation. We have one equation for the position, one for the velocity, and one for the acceleration. Here B coefficients, and here C coefficients. We measure only the distance. So the velocity and the acceleration are not measured by the filter. They are estimated, but they are not measured. If we look at the response, which represents the state trajectory by time, we see that, as you see, this is in blue, the distance and how it moves discretely. This is the velocity. It is changing, as we said, it is not constant. And in green, you will see the acceleration, which is not exactly constant. It is, as you see at the end, there's some deviation shown clearly as a result of course, or of the impact of the surrounding media, such as the wind, or such as the temperature, or any other noise, which causes the acceleration to change. So in this case, there is a forcing variable, which is the acceleration effect, while in the previous case with constant velocity, there was an input also, a forcing input, which is a result of the change of the acceleration. But here it is as a result of change of the effect of the jerk. So this is the time representation, which shows you how the dynamics of Kalman filter with a constant acceleration model. Note here that the number of states is 3. So this matrix will be 3 rows by 3 columns. And here also B must be 3 columns, sorry, 3 rows. C and D, 3 positions, as you see here. We measure only one of them. The D is not applicable. We do not have a direct input connected directly with the output. So these are the 3 common cases which we can face. Now, the questions arises. When we are obliged, or when we want to work with the constant velocity model, and when we to work with the constant acceleration model. Constant velocity model is chosen when the target moves smoothly. Here we are assuming that we are working with a tracking system. But as I told you, this is not only applicable for motion control. It is applicable for any variable. So when the variable of interest changes smoothly with little acceleration and a constant acceleration model is used when the target often speeds up and slows down or maneuvers. So it changes directions with acute angles, with accelerations frequently done and decelerations frequently done. We use the constant acceleration. Constant velocity is simpler and more robust for steady motion, while constant acceleration captures richer dynamics but requires more states and careful tuning. In other words here, the most characteristic things for the constant velocity Kalman filter, it assumes the object moves in a straight line, like a car moving in a highway, for example. The model here is very adequate. It is best for targets with predictable uniform motion, like car on a highway or satellite, for example, in an orbit. It uses smaller state vector. Yes, because we need only two variables. And it is less sensitive to noise and easier to implement. Yes, it is less sensitive to noise because only the velocity is assumed to change. The constant acceleration model assumes velocity changes linearly. The changes are linear due to constant acceleration. We have a constant acceleration. So the velocity changes linearly. If we have constant acceleration, the velocity changes linearly. It is suitable for maneuvering targets which makes maneuvers, such as aircrafts or robots or other similar objects. The state vector here is not only two elements, position and acceleration, it includes also and velocity, it includes also acceleration. So it is larger vector, position, velocity, and acceleration. And it is more accurate in dynamic environments where are maneuvers taken, but more computationally demanding. Here is a table which shows a comparison between them. The state vector for constant velocity. Usually we take x as the position and y as another position. Here we are talking about constant velocity, two-dimensional model. So this model moves the object in a plane, x and y, and the other two variables, the velocity by x-axis and the velocity by y-axis. If we talk about constant acceleration, we have three variables because we have axis x, axis y, velocity at axis x, acceleration at axis x. These are three values, three variables, and y, velocity at y-axis and acceleration at y-axis. So now we have 3 and 3, 6 variables. Constant velocity is best used for smooth, steady motion. Constant acceleration for targets with frequent speed changes. The advantages of CV, it is simple, robust, and low noise sensitivity. The advantages of CA captures richer dynamics and gives better accuracy. I think this is the most important. Limitations, poor acceleration maneuvers. This is the existence of acceleration maneuvers. This is the cause of the instability of the velocity, of course. And for the constant acceleration model, the matrix is larger because the number of the variables becomes 3 in a constant velocity, one-dimensional motion, and it becomes to 6 as we have 3 coordinates or variables for one dimension for the x and other 3 variables for the other dimension. This is what I wanted to tell you about the dynamic models in Kalman filter. So as you see, sometimes it makes sense to begin modeling the filter by using constant velocity. And if you find that it is giving not acceptable results or not accurate results, you can change the parameters to constant acceleration model. Now you know the areas where we select constant acceleration and where we select constant velocity, and how the matrices are found, and you have an idea about their performance as a time response or as a state trajectory. Okay, with this I finish this lecture. Wishing you the best and see you in the coming lecture. Goodbye.